everyone. In this video we are going to learn about the second type of integrating factors for a non-exact differential equation. So this is a continuation to the category reducible to exact, and we are going to discuss integrating factors for non-exact differential equations and how to make them exact. So this is the second rule. In the first rule, in the previous video, we had seen how to find out integrating factors of the form x to power p y to power q for making a non-exact differential equation exact. Now this is the second rule, which has two versions, 2a and 2b. The first version, 2a version, says that suppose there's a differential equation that you start with, let's say m dx plus n dy equal to 0 is a non-exact differential equation. Now if it's non-exact, then that means the equality of these two partial derivatives won't be there. Del m by del y won't be equal to del n by del x. So these two partial derivatives are unequal, and that's the reason of non-exactness of this differential equation. Now if these two are non-equal and we want to find out an integrating factor, that means we want to find out an expression involving x and y such that the non-exact differential equation, when multiplied with that expression, makes it exact, and then we can solve it the exact way. Then there are two versions of this second rule. The first version, 2a version, says that since these two partial derivatives are unequal, their difference will be something non-zero. You consider the difference, del m by del y minus del n by del x. Now this difference obviously will be non-zero, and what you do is you divide this by this function which is appearing in the second derivative in this difference term. So whatever is appearing as the second term in this bracket, that particular function goes in the denominator. If 1 by n times this difference of the partial derivatives is a function of x only, let's call this as a function of x only, let's call it as p of x, then the rule says that e to the power integral of this function serves as an integrating factor for the differential equation. So what you do is, since the equation is non-exact, there is this equality of partial derivatives is not there. That means the difference of the partial derivatives is something non-zero. You divide that non-zero thing by the second function here, n, and suppose this entire thing after simplification boils down to something involving x only, and we call it as px or something involving x. Suppose the notation is px, which we use here, then e to power integral of this function of x serves as an integrating factor. There's another version. This is the 2a version of the rule. The second version of the same rule is that instead of dividing by n, what you do is you reverse the order of these two partial derivatives. Instead of saying del m by del y minus del n by del x, you reverse them. You just take the negative of the expression that you took in rule 2a and then divide by the second function. The second function happens to be m here. And suppose this is a function of y only. After simplification, suppose you figure out that everything is cancelling, you're just left with something involving y, say qy, then e to power integral of this qy is an integrating factor. So it's a very easy rule. Since the given differential equation will be non-exact, the difference of the partial derivatives will be non-zero. You try dividing by n first. If that happens to be a function of x only, then e to power that expression's integral serves as an integrating factor. Now you reverse the partial derivatives here and divide by m. If this serves as it's just a function of y, then you take e to the power integral of that function of y, and that serves as an integrating factor. Let's understand these two versions of rule 2a and 2b through one or two examples here. Let me start with a question where, let's say you are given a differential equation 2x square plus y dx plus x square y minus x dy equal to 0. Suppose this is the differential equation given to us and we are expected to solve it. Now let's see what is m comparing with the standard form m dx plus n dy equal to 0. This expression is m, this expression is n. Now for checking exactness, we find out the partial derivatives. Del m by del y. Let's see what is del m by del y. This is just a function of x, so this won't contribute to del m by del y. The only thing that comes from here is the derivative of 1 with respect to y, that's y with respect to y, that's 1. Now let's see what is del n by del x. Del n by del x, when I partially differentiate n with respect to x, that means it's going to be 2xy minus 1. So that's the partial derivative with respect to y of m, and this is the partial derivative with respect to x of n. Since these two are unequal, the given equation is non-exact, as del m by del y is not the same as del n by del x. The given equation is non-exact. Now if non-exact, there are ways of making it exact. In the previous video we had learned how to find out an integrating factor of the form x to power p, y to power q. We can apply that rule also here. It's going to work well, but let me exhibit rule 2 here. You can see there are questions which can be done using 3-4 different ways. It's up to you which approach, which procedure you like the most with respect to calculations and ease of the procedure. That particular approach can be followed by you. All of them are going to land you into the same solution set. So let's not do it using rule 1, which we had discussed in the previous video. Let's try applying rule number 2, which we are learning in this video right now. So for that, what do? We just observe the difference. The partial derivatives are not equal. Let's examine the difference. What will be the difference? 1 minus 2xy plus 1. If you look at the difference, del m by del y is 1, del m by del x is 2xy minus 1. So you just find out the difference between these two partial derivatives. That happens to be 2 minus 2xy. Now once you have this difference, which obviously will be non-zero because the equation is non-exact, then you look at your m and n and see whether 2a will be applicable or 2b will be applicable. When is 2a applicable? If on division by n, the difference on division by n lands into just a function of x. Y should not appear. Now look at this expression. It's 2 minus 2xy. If I divide it by x square y minus x, let me see what happens if I am doing the difference del m by del y minus del n by del x divided by n. This difference turned out to be 2 minus 2xy, and I am dividing by n. N is x square y minus x. If this simplifies just to a function of x, then things are working well for us. So let's see. 2 is common above. We are left with 1 minus xy after taking 2 common from the numerator, and here x is common, so you have xy minus 1. Luckily these two cancel out and you are left with minus 2 by x, a function of x only, and that's when your rule 2a is applicable. 2a says that when you divide the difference del m by del y minus del n by del x by n, the difference divided by n should just be a function of x, and that's what is happening here. It's just a function of x, and according to the rule, our integrating factor this time will be e to power integral of this function which has appeared here, and we know that the integral of minus 2 by x is minus 2 log x, and by using the property of logs, this minus 2 goes here, it's this, and since e and log are reciprocals of each other, inverses of each other, so we can just write it as x to power minus 2. Therefore 1 by x square is an integrating factor of the given non-exact differential equation. Now what is an integrating factor? An integrating factor is an expression with which you multiply a non-exact differential equation, and that makes the non-exact differential equation exact. That means if you multiply the given equation by 1 by x square, this was the given equation, 2x square plus y dx plus x square y minus x dy. Let me copy it down. So the given equation, multiplying the given equation by 1 by x square, the resultant equation becomes this. The equation was 2x square plus y, so you are multiplying by 1 by x square, so that's your new m dx, plus n was x square y minus x, and you're multiplying by 1 by x square, so x square appears here. So this is the new equation that you get. Now simplifying it a little bit, you can see it's 2x square by x square is 2 plus y by x square dx, plus similarly x square cancels here and you're left with this. And if for your own satisfaction, you can verify that this new equation is an exact differential equation. And that's what integrating factors are. You do not have to verify again, but for your own satisfaction, as we are doing this as the first question of this type, you can verify that this new equation is exact because you do have partial derivatives equality now. So since it's an exact differential equation, the solution is given by, we know the procedure of solving exact differential equations. We integrate this with respect to x, treating y as a constant. So the integral of 2 becomes 2x plus y is a constant, and the integral of x to power minus 2 is minus x to power minus 1. So it's minus y by x. And then from here you take terms which are not involving x. So y is the only term of that type. So here you get a y square by 2, and that's equal to c. That's the standard procedure for solving an exact differential equation. So effectively you can write your solution as 2x plus y square by 2 minus y by x equal to c is the general solution of the given differential equation. So that's how you apply rule number 2a when the equation is non-exact. You could have done it using the previous rule also. You could have assumed an integrating factor of the form x to power p y to power q, and the same working which we had in the previous video would have led to this integrating factor x to power minus 2 through that procedure also. But this whatever, it's just that your wisdom with respect to ease of calculation and the ease of process is going to be used whenever there are more than one option is there. Suppose there's more than one option for solving one particular differential equation. It's entirely up to you which procedure you would want to follow. Whatever you feel is better, you can apply that. So let me demonstrate one more example here to make it better for you with respect to understanding of the rule, because 2a is what works well here, and in fact rule 1 would also work well here. Let me take one more problem. Suppose the question looks like 2x plus tan y dx. Suppose this is the question, x minus x square tan y dy equal to 0, and we are expected to solve it. Now the format, whenever we see an equation in the form m dx plus n dy equal to 0, we are prompted to check its exactness, and if it is exact, we are prompted to use the procedure of solving exact differential equations to solve it. Now suppose we check exactness and it turns out to be non-exact, then this video is going to help you make non-exact differential equations exact. Do not assume that all non-exact differential equations can be made exact, but yes, there are a specific class which can be made exact using either rule 1 or 2a or 2b. I'm going to discuss one more rule in the next video, but for now these are the rules which are available for making non-exact differential equations exact. Now let's see, whenever we see an equation of the form m dx plus n dy equal to 0, we check the partial derivatives del m by del y. What is del m by del y in this case? It's going to be secant square y. The partial derivative of m with respect to y is secant square y. Del n by del x, here we have to differentiate with respect to x. So first term gives a 1, and here you have a minus 2x tan y. Now when you do, you see that these two are not equal. The partial derivatives are not equal, therefore the given equation is non-exact. Now if it is non-exact, either you try some other approach which you know for solving such a differential equation, or you can try making it exact. Now since it does not involve powers of x and y only, so we are not prompted to use rule number 1. We are prompted to use rule number 1. That means we try an integrating factor of the form a power of x times a power of y only when m and n are involving powers of x and y. That's the prompt for us, as we discussed in the previous video also. Now let's see if we can apply rule number 2a or 2b in this setting. Now for that we need to check the difference, del m by del y minus del n by del x. Let's see what is the difference between these two. It's going to be sec square y minus 1 plus 2x tan y. When I subtract, I take the difference between these two partial derivatives, and we know that sec square y minus one is tan square y, so it's tan square y plus 2x tan y, which I can write as tan y is common, so I can write it as tan y plus 2x. Now our job now, after looking at the difference, we have to observe whether on dividing by m or n it's simplifying. Now if this difference on division by n leads to a function of x only, then our rule works well. If this difference on division by m leads to a function of y only, then the rule works well, otherwise we'll have to try something else. Now you can see that 2x plus tan y is common in the difference, and here also 2x plus tan y is appearing, so division by m is going to work well here. Now mind it that whenever you divide by m, this partial derivative with respect to m should be reversed inside, so it should come as the second term. When you're dividing by n, this should come as the second term, del n by del x should come as the second term. When you're dividing by n, this should come as the second term. So I am reversing these two derivatives, the difference, so it becomes minus tan y plus 2x, and on division by m is tan y plus 2x only, and that's the reason I'm dividing by m, because it's going to simplify, cancel this out, and we are going to be left with just a function of y. Only y is involved in this expression, so my integrating factor according to rule 2b is going to be e to power integral of minus tan y dy, and we know that it's equal to e to power minus log of sec y is the integral of tan y. So that means log and e, and using the property of log, I'm going to take this here to the power, so my 1 by sec y is going to serve as the integrating factor. So multiplying the equation by integrating factor, the definition says that it's a factor which on multiplication makes a non-exact differential equation exact, and that is the intent of finding integrating factors. We are looking for factors which on multiplication make non-exact differential equations exact. So 1 by sec y is going to serve as an integrating factor according to the procedure which is stated in rule 2b. So multiplying the given equation by 1 by sec y, we get, what do we get? The given equation was 2x plus tan y dx plus x minus x square tan y dy. So let's see. So it's 2x plus tan y by sec y, because I'm multiplying by 1 by sec y, that's my dx, and then with dy my new n becomes, n was x minus x square tan y, so it becomes x minus x square tan y, and I'm multiplying by 1 by sec y, so sec y goes here. So this is my new equation, which I can simplify a little bit to write it as 2x cos y plus tan by sec. So it's sine by cos, so it's sine y dx, plus here I have x cos y, and here I have x square sine by cos, and again you have a sine y dy equal to 0. You can see that this new equation is now exact, because that's what the rule is stating. You are finding this 1 by sec y just because you want the new equation to be exact. So if for your own satisfaction you can check that this new equation does have equality of partial derivatives, it has become exact. Now the solution, which is an exact differential equation, so the solution is given by, for exact differential equations we had discussed in a previous video, the solution is given by, you integrate this with respect to x, treating y as a constant. So y is a constant, so 2 cos y is like a constant, so integral of x is x square by 2, so I'm going to write it as 2 cos y x square by 2, and here integral of sine y with respect to x, treating y as a constant. If y is a constant, sine y is also like a constant, so you get this as the integration. Now here, from here you have to pick those terms of n which are independent of x. Now this very much involves x, this very much involves x, so that means n star is 0, there is no contribution from n, and according to the procedure the final solution is given by this, and obviously this 2 cancels, and the general solution for the equation is given by x square cos y plus x sin y equal to c. So that's how we solve non-exact differential equations. Let me quickly give you a recap of the three rules that we have discussed, rule 1, rule 2a and rule 2b. Non-exact differential equations, how do you identify non-exactness? You see that del m by del y is not the same as del n by del x. Then you try finding out integrating factors. Now there are three processes which we have learned in this video and the previous video put together. One of the rules is that you try an integrating factor of the form x to power p, y to power q, and this generally works well when m and n are involving powers of x only, x and y only. Now the second rule is that you take the difference of this, these two partial derivatives, you take the difference, and when you divide it by the piche wala, the second one, the second expression, it's like 1 by n should appear here, and if it is a function of x only, then this, let's say px, call this function as px, then e to power integral px is going to be an integrating factor. That's rule 2a. This was rule 1. You try integrating factor of the form this is rule 2a, where you take the difference of the partial derivatives and divide it by the second function n, and if this overall expression turns out to be a function of x only, then this is an integrating factor. And in rule 2b is very similar to 2a. You just reverse the roles of m and n here. You take the difference with the partial derivative with respect to m appearing as the second term and divide by m. If this is a function of y only, let's say qy, then e to power integral qy dy is an integrating factor. So that's how you make non-exact differential equations exact. These are the three processes which help you to find integrating factors for certain good, nicely behaving non-exact differential equations. By nicely behaving, I mean that you can look for certain expressions which on multiplication make these non-exact differential equations exact. Do not assume that every non-exact differential equation can be made exact, but yes, there are certain good class of non-exact differential equations which behave well. They become exact when we multiply them with suitable expressions, and those suitable expressions are called integrating factors, and these are the three rules that we can adopt for solving non-exact differential equations after making them exact. There's one more rule which is applicable to homogeneous differential equations, so that will be taken up in the next video. For now, that's all for integrating factors for non-exact differential equations. Thank you so much for watching.